let me explain the swapping in just a little bit more detail. That way you understand why we need a little extra memory in order to make this work. So let's say we want to swap the values of x and y. So I'm just going to put it up here. So here is x. That's not a good x. Okay, that's not a good x. Let's try again. Here we go. Here's x, and here is y. There we go. Now let's say we want to store the value of y into x. So I'm going to do a little arrow here and say, okay, we're going to take y and we're going to store it into x. Well, you might think, well, let's just take the value of x and then store it into y. But what happened here? We took the value of y and stored it into x. That means the value of x is gone. So if I try to store x into y, I'm just going to put whatever y was and put it back into y, which doesn't really help. We just obliterated the value of x. So this doesn't help. So yeah, so this is no good. No, that doesn't work. So let's just get rid of that. Okay. So what we do instead is we'll copy y into a temporary location t. So let's try this again. So let's say I have x here. That x looks a little bit better. We'll just go with it. We have a y here, and I'm going to put a t right here. So there's our temporary value. So what I'm going to do now is I'm going to copy y into t. And then finish the arrow here. There we go. So now t has the value of y. And this means the value of x is preserved. We haven't obliterated it. So now we can copy x into y. So I'm going to take x, I'm going to copy it over to y. And sure enough, that does get rid of the value of y, but y is in t. So we have that value preserved. So now we can copy t and store it into x. So now x has the value of y, and y has the value of x. So we have now successfully swapped the two values. And all we had to do is just have one memory location to let us temporarily store one of the two values. So now we can ask ourselves, what is the order of magnitude for this algorithm? Well, let's take a look back at the number of comparisons. We said it was n minus 1 over 2 times n, and that equals 1/2 n squared minus 1/2 n. So if C handles all the constant operations like we did before, then the total work is Cn squared. Now why is the work n squared and not like n squared minus 1/2 n or something? Well, that's because the main part of the number of comparisons is this 1/2 n squared right here. That is much larger than the minus 1/2 n. In fact, when n gets really large, this number just does not become, it's not important. It does not become important. It's negligible. So we can just cross that out. So the big part is the n squared portion of the number of comparisons. And 1/2 here is a constant. So we're not too worried about the 1/2 part either. So we'll just cross that out. So all we really care about is the n squared. So our total work done is Cn squared, which means that the algorithm is of order of magnitude n squared, or as we use with the notation we talked about before, would be theta of n squared. And what this means is as the size of n grows, the amount of work grows at a rate of n squared. And that means a theta of n squared algorithm grows much faster than the sequential search algorithm that we had before. Because remember, that was theta of n. So theta of n means that we grow at a linear rate, but here we're growing at a rate of n squared. Now you might think, okay, n squared, that doesn't sound too bad, right? Well, why do we care about this? Why is this important? Well, let's do some comparisons. Let's compare 0.25 n squared with something like 10 n. And I think, well, that shouldn't be too bad, right? Well, when n is 1, 0.25 n squared is 0.25 and 10n is 10. So here it looks like 10n is definitely a lot larger than 0.25 n squared. So no problems there. All right, let's increase the size of n a little bit and just see what happens. Well, let's say n is 10. Well, 0.25 n squared is now 25, and 10n becomes 100. Okay, still no issues there. I mean, 10n is still larger. All right, what about n is 25? Well, that means 0.25 n squared is 156.25, and 10n is 250. Okay, no issues here. I mean, 10n is still larger. I mean, no problems here comparing n and n squared. What if n is 40? We find that 0.25 n squared is 400, and 10n is 400. So that means when n is 40, the values of 0.25 n squared and 10n are the same. So what we're seeing here is that the n squared number is growing faster than our n value. So now what we're going to end up seeing is the value of 0.25n squared is going to start becoming larger. So here when n is 100, 0.25n squared is 2500, while 10n is only 1000. So here we're starting to see where it's surpassing. And then let's take it another step. Let's say n is 1000. Well, 0.25n squared is 250,000, and 10n is only 10,000. That's a huge gap, and this gap is going to grow even more and more as n becomes larger. I mean, just try this out on your own. See what happens when n is like a million. I'm going to tell you that's going to be a very large number for 0.25n squared, whereas 10n, well, that's only going to be 10 million. Whereas 0.25n squared, it's going to be a lot larger than that. So we see that with an n squared algorithm, it's going to take a lot more time when n is substantially large compared to an algorithm that is theta of n time. So what does this all mean when it comes time to deciding an algorithm? Because remember, we talked before about if I have multiple algorithms that solve the same problem, are there some algorithms better than others? And the answer is yes. If we have two or more algorithms that perform the same task, we want to pick the one with the smaller order of magnitude. These algorithms are normally a lot faster, especially when we consider very large input sizes. You may not see the difference when the input size is like a very small number, like 10 or 100 or even 1,000, but we could see the difference when n is much larger, like a million or 10 million or a billion. And there are cases where we do get values that large. We may not see it ourselves, but it can happen. So we got to keep in mind, we want to pick the one with the smaller order of magnitude so we can deal with those much larger input sizes. So in this case, selection sort takes theta of n squared time. So we can say that this algorithm really isn't that great. In fact, there are much faster sorting algorithms than selection sort, but here we talked about it because A, it gives us an example of a theta n squared time algorithm, and B, it's a very simple algorithm to understand.